So in this example we'll continue with the previous project, the allotment, but we're going to add some groundwater in this case. And we know that the average yearly minimum is at 11 meters above datum of the groundwater, and the groundwater reaches an average yearly maximum of about 13 meters above datum. And now we will see what the impact is on the infiltration conduit of the previous exercise. So we're going to complete this in Sirio. So I've loaded the previous exercise, so we still have the infiltration capacity and etc. all defined, but now we're also going to account for groundwater. So I use this checkbox and then I can define the groundwater level for the entire project using this button. So in this case we'll go for option 2. We add some seasonal variation based on the minimum and the maximum level. The minimum level is at 11 meters above datum, and the maximum water level or groundwater level is at 13 meters above datum. And on the right hand side you can see here which water level time series or groundwater series is being simulated. So that means that at the starter of the second quarter of the year we'll have the highest groundwater level, and at the start of the fourth quarter we'll have the lowest groundwater level. And then Sirio asks me to keep the current groundwater levels and only use this newly defined groundwater level for all new reservoirs. So if I select this option, we will not change any groundwater level of all the existing reservoirs. So basically we will not use or simulate the groundwater drainage. And on the right hand side, the second option is reset all the groundwater levels in the entire model to this new level. And of course we'll go for this option in this case. So now all the groundwater levels are being reset. And then I go back to the model and you'll see that there are some parameters missing. That's why this parcel module is shown in red. So if I click on this button, I go to the parcel module, which represents one house, and you can clearly see here that there is a parameter missing, and in this case the floor level of our infiltration basin is also not defined yet, and that's also needed. So in this case I assume that the groundwater level, that the floor level of the infiltration basin is at 13 meters above datum, which is just at the maximum level of the groundwater. So basically there will be no drainage in the infiltration basins of the parcel module. And then if I switch to the parameters of the infiltration conduit, I see that all the parameters are already well defined, and we will also simulate some drainage here. And using this button I could change the groundwater level of this specific reservoir only. So it is possible to use different groundwater levels for different reservoirs and also different for the parcel module. So then I can simulate the model and see what the impact will be of the drainage of groundwater. And here we see that we have a totally different mass balance. For now we have a much bigger inflow, and about 79% of all the incoming flow will consist of drainage of the groundwater. So that's very dramatic. For the reservoir, 89% of all the incoming flows will actually consist of drainage of groundwater. So that's very significant. The infiltration is very small now compared to the overflow volumes, which are much higher. So 80% of the entire volume passing into our infiltration conduit, and that's mainly drainage, will go through the overflows. We will have a lot of overflows in the system. You can also see that here on the right hand side. So now we have many overflows. We have about 1000 independent overflow events over 100 years, and the overflow volumes are also becoming very large, of course, due to this drainage. You can also inspect some individual time series, for instance for the infiltration conduit. If we go for the water level, you can clearly see that there are some periodic changes, and these periodic changes or fluctuations are also matching the groundwater level that we have defined. So now we'll use a different design. We will try to prohibit infiltration, so we are deviating from our design using an infiltration conduit because it was very clear that we have too much drainage in this case. So we will look at two alternative designs that do not rely on infiltration. So it will be solely buffering and a true flow to a more downstream system. And the first design has an orifice with a diameter of 150 millimeters, and it's located at the bottom of our conduit. And the second design looks at a hydroslide, which can give us a constant flow of about 5.5 liters per second. So the dimensions of the conduit itself is not being changed, but we are prohibiting or impeding infiltration and adding two different kinds of through flows in our design. So let's switch back to Sirio, and then we will also model it here. So first I will copy the existing reservoir to create an alternative, and this will for instance be my orifice. Then I immediately switch off infiltration, so I do not account for infiltration anymore, and I do not account for drainage. And then I will add the through flow. I will simply let it flow to the surroundings, so external, going to a different system outside our model. I create the new connection, and it is an orifice. And then I can define the parameters over here. It has a diameter of 150 millimeters, and the invert level is at 12.3 meters above datum. So this is located at the bottom of our conduit. Save and exit. And then I can also define the second design. So again, I copy our reservoir, and this will be our hydroslide. So I also give it a name to make it a bit easier to compare later on. And the type of through flow relationship isn't an orifice in this case, but it is considered to be constant with a flow of 5.5 liters per second. So now I've created our two different designs. So we still have our infiltration conduit, which uses infiltration and drainage, but now I also have two alternative designs that do not use infiltration. They have the same dimensions, but there is for each a through flow. For the left one it's an orifice, for the right hand side it's a constant flow. So then I can simulate the model again, and we'll compare the results. So here we can see the mass balance. It's very important to note that the column total can be ignored in this case, because the column total will be the sum of all the different reservoirs that we have in a system, and we're looking at alternative designs, so that doesn't make any sense anymore. So do not look at the column total when comparing different designs. So we can easily minimize this column. And then if we look at the different reservoirs that we have, so the infiltration conduit and the two orifices, and the orifice and the hydroslide, we see that we do not have any drainage anymore for the two new designs. So we also do not have infiltration, of course. And basically the parameters will look more or less the same. So that means that all the incoming flow is going through the through flow in this case. But we can already see that we have a big difference in the maxima water level that are being simulated. So in the hydroslide we will have a higher maximum water level that is reached. We can also see that here in the overflows, for instance. So here you can see the overflows for total. So again, that does not make any sense because we're comparing different designs. So let's look, for instance, at the hydroslide. And we can see here that we have one overflow event in 100 years, and it's only just above 1 cubic meters. So it's a very, very small overflow event. Then if we look at our orifice design, we see that we even have not a single overflow event in 100 years. You can also see that in the degree of filling. So in this case, when we use an orifice as outflow, our system will be filled maximum for 39%. So that means that this part of the storage is actually never used, not even in 100 years. So it's this conduit is actually too big for this specific orifice. The orifice is actually too big. Then if we look at the hydroslide, we can see that we have a much better degree of filling. So actually the total storage is being filled in this specific case, and it's reaching 100% once in 100 years. Then you can also see here the flow distribution, which shows us what the maximum overflow and through flow discharges are. Of course, for the hydroslide, we said that we could allow a through flow of 5.5 liters per second maximum. You can also see that here, it's actually 5.5 liters per second maximum. But for the orifice, we see that we have a much higher through flow, reaching about 20 liters per second. So in fact, this is much higher than expected. So that means that this through flow combined with this conduit is actually way too big for the design. So it doesn't make any sense to design such a huge conduit together with such a big through flow. So that's why we'll redesign this project once more in the next exercise, and then we will look at 2 ditches instead of this conduit with some buffer to get a better design.